As the concept in this course are very well learned via examples and exercise, I urge you to do as much examples as you can, and we'll have several examples now. So we want to determine the PDF of y equal g of x in terms of the PDF of x in several examples. Some of the examples we have solved in different methods. You want to use this procedure and apply it. In this example, I consider a linear transformation, and I want to find a PDF of y in terms of PDF of x. The first thing I do, I calculate derivative of y equal to g of x is ax plus b. So the derivative of these is equal to a derivative of these. And if you want to solve this one, you get y minus b divided by a equal to x, because if you subtract this equation b from this equation, you get 1 minus b, y minus b, and then you can divide it by a, provided that if a is not 0. If a is 0, then this solution is not true. So if a is 0, then you don't have this one. So y equal b is your only solution, and in this case. So because you have a unique solution for a is not equal to 0, so you get fy of y is equal to fx at the solution, which is here, and then divided by this derivative, which goes here. Remember that this one I write it in terms of y, so obviously this guy is equal to a, so it's going to be fx of y minus b divided by a, and then divided by absolute value of a. Remember to put absolute value here, because the PDF is never negative. This guy is not negative, so you have to put absolute value to make this one positive. So this is the general formula that we have obtained. For a equals 0, we obtain delta of 1 minus b, which is equal to limit of whatever you have here when a tends to 0. Let us have a second example. In this example, I consider this function. For this function, I calculate the derivative, so the y equal to 1 over x. The derivative of this dy over dx is equal to 1 over x to the power of 2 minus, but I have to put absolute value of that, so I get this absolute value. This minus will disappear, so this is why I have this one. And the inverse of that, so y equal 1 over x. If I want to solve it, from here I get x equal to 1 over y. So I always get a unique solution, provided that y is not 0. So if y is 0, then I don't have a solution. So in this case, fy of y is always equal to, because it's a unique solution, I get fx of the solution, which is 1 over x. Okay, but this 1 over x, I have to write it in terms of y, because 1 over x is, fx of solution. So y is equal to 1 over x. So PDF of y is equal to the PDF of x at solution and the derivative of g with respect to x when you replace x by solution. So what I do here, so I get fx solution here is 1 over y, so I replace 1 over y here, and this derivative is equal to 1 over x2. Here 1 over x2 is equal to y2, because 1 over x is equal to y. So therefore I have to replace this guy by y2, and this is why I get this solution. So in this example, is if x has a Cauchy density with parameter alpha, let's see what will be the distribution of y. A Cauchy distribution is given by this function. So if I want to find fy of y, because of this function, I could use this formula. So I have 1 over y2 fx of 1 over y. So that means that I have to replace in this x by 1 over y and then put it in this equation. So I get 1 over y2 times 1 over pi, and then get alpha. Instead of x, I have to put 1 over y to the power of 2 plus alpha 2. If you simplify this equation, you get this one. And obviously, you see that this formula is same as this formula, just you replace alpha by 1 over alpha. So the new random variable y has also a Cauchy density, only the parameter instead of being alpha is 1 over alpha.